So this lecture is about 3D moments. So we have a force in a three-dimensional space, and then we want to find a moment about the point. So let's just consider a scenario. We know this is point A. The force is going from point A to point B. I'm going to call the force FAB. Now I want to find the moment from force FAB about a given point, like point O somewhere here. That's my plan. So if I want to find moment about point O, again, you remember already we talked about moment is equal to force times perpendicular distance. Now there is something called, we call it cross product, or external multiplying of two matrices together. It's too much for you because you may not have any like mathematics background on this, but there is no worriness. So I'm going to just use the alphabet for it. So moment of force AB about point O. So I'm just clear, right? So I want to find moments from force FAB about point O. I'm going to say this will be an R. R is the position vector, cross with an F. The F, which is FAB. That's the easiest way. We already know FAB again. In the past lecture, you learn how to get your FAB in IJK component. So the R is the position vector. Position vector always starts at the point, in this case is the point O, and goes to the force. So again, I'm going to just put something here for myself. This start at point and then end at force. So R start at O, end at either A, either B. It doesn't matter. If you use any of them, you get the same answer. So I'm going to ROA. I'm going to put the vector symbol up there, or can start from O, go to B, cross with FAB. So again, but using like this, it will give me, again, this symbol here is the cross product. I'm going to tell you how to do a simple cross product. There are two methods we discuss. One method would be the vector approach, which is, again, cross product. The other method is the method for a scalar approach. A scalar approach is the method that I'm going to teach you how to multiply, how to find perpendicular distance for something. Let me start with the vector approach. On the vector approach, we say, okay, M is equal to R cross with F. So I can say I, J, K. This is symbol is for determinants. Now I'm going to put here Rx, Ry, Rz, and then down here we put Fx, Fy, and Fc. So how we do a cross product? The cross product, the way that works is because again, if you have cross product of two, like if Rx, Fx, if the force is on the x, the distance is on the x, there is going to be no moment produced. So when we consider I, like when we want to do the calculation for I, we consider everything except the I. I'm going to say that. What does that mean? If I put my pencil here and here, what I'm going to be ended up at, again, because I'm talking about I, I'm going to neglect the column for I, and then we neglect the top row. So I got R, Ry, Fz, Rz, and Fc. So we are actually breaking down a 3 by 3 determinant to 2 by 2 determinant. So again, if I put my pencil here and here, what you could see Ry, Rz, Fy, Fz. So I'm going to put here Ry, Rz, Fy, Fz. Okay, for the J, you have to use a negative J, and then plus K. What I'm going to use for J, on the J, I'm going to put my pencil on the column for J. I got Rx, Fz, Rz, Fx. So I'm going to put them here. So I'm going to get Rx, Rz, and then fx, fz. So keep it like this, and then if I put my pencil on the k, I'm going to get rx, ry, fx, fy. Rx, ry, fx, fy. So, but again, I already know that if I have a little determinant like this, a, b, c, d, your answer is equal to ad minus bc. So all I need to do for these little determinants, I have to say this times this minus this times that. So this will be ry fz minus rz fy. I'm going to repeat the same thing here. So for j will be rx fz minus rz fx. And the last one is rx fy minus ry fx. So this is actually the cross product. That's what I taught you is a method in like calculus 3. We talk about if you have two vectors. Again, in this case, what does these two vectors mean? One of the vector is the force. One of the vector is the position. Right? If you go from ROA, in this case, if you cross multiply these two, you use all this time this 3, this symbol of this 3. Again, I'm going to put my finger here. So if this is your force, this is your distance, my thumb is going to be the moment. So basically, these 3 has to be perpendicular together. When we go to a scalar approach, I will open up this stuff more. But this is F, the force, the position. So if you cross multiply this, you're going to get the moment. And we already said that the distance and the force, they have to be perpendicular together. And this is the mathematical approach of it to do the calculation. So let me pick up a problem and then we go ahead from there. So the problem that I want to pick up is, again, it's very similar problem that we did last week. And then on that problem, we find the component of f of y. I'm going to use that. So go 2 more pages. So this is what I have. In this problem, I have a force of f of b, which is going from a to b. And I want to find the moment of FAB about point O, which is origin. So that's what the question asked me. The question asked me to find moment of FAB about point O. For me to do that, I'm going to just write it at R cross with F. R with the start from O. I need to make a decision to go to B or to go to A. It doesn't matter. You can pick either to go to A or to B. I like the A more. It's just because the coordinate of point A is 0, 0, 6. It doesn't make a difference. And point B, the coordinate for point B is 0, 2.5, 0. So I'm going to say ROA cross with FAB. I need to go to the last session. In the last session, we discussed how to calculate, how to bring the FAB to IJK component. So I need to work on that right now too. So FAB is going from A to B. So FAB is going from A to B. So I need to find vector AB, so vector AB is B minus A. And then I have here B minus A is 0. Minus, again, you remember that B minus A is XA minus XB, which is 0 minus 0. And then I have 2.5 minus 0. And then lastly, I have 0 minus 6. So I'm going to get AB is equal to 0. And then we get 2.5 and minus 6. So once you have AB, you get UAB if you remember. UAB is equal to AB divided by magnitude of AB. So AB is 0I plus 2.5J minus 6K. I'm repeating this on this line. And then over the magnitude of that is 2.5 to the power of 2 plus 6 to the power of 2 plus 0 to the power of 2, right? That's the length of that vector. So I'm gonna look into to see what I found for this. So if you simplify this, you're gonna get 6.5 for it. So let's keep it like this, and then I'm gonna have FAB is equal to magnitude of FAB into UAB. So the magnitude is 780 Newton, 780 Newton into this 0I plus 2.5J minus 6K divided by 6.5. The easier way is just to divide this by that. So 780 divided by 6.5, that will be 120. So this divided by this is 120. So I'm going to get FAB is equal to 120 times 0 will be 0, I, plus 120 times 2.5, which is going to be 300. 300J minus 6 times 120 is 720K. Or in other language, out of this 780 force, so you can see 300 of it is on the Y, and then minus 720 is on the Z. So I found FAB as 0, 300 minus 720. I need to find ROA. So ROA is equal to A minus O. Remember, always end minus beginning, right? End minus start. So in this case will be 0, 0, 6. Again, O is 0, 0, 0. So I have these two. I like to do my determinant. So I'm going to say moment of force AB about point O is equal to ROA cross with FAB. And in this case I have I, J, K. So ROA is 0, 0, 6. And this one is 0, 300 minus 720. Now it go back to the little determinant that I showed you. So you put I minus J and K. So if you cover the I, you get 0, 6, 300, 720, right? So in this little determinant, we already talked about that. If you have a little determinant, A, B, C, D is AD minus B, C. So if I cover it like this, so this will be AB will be 0 into minus 720, and then minus 6 times 300. I'm going to go to the J. If I cover the J, I'm going to get 0 this, 0 that. So actually 0 times everything will be 0. So, but again, I'm going to just, because I'm showing you what's happening. So I'm going to cover the J. I'm going to get 0 times minus 720. And then the next one is minus another 0 down there into 0 times 6. I'm doing for the last one. In the last one you cover this. You get again 0. 0 times 300. Minus 0 times 6. So overall, if you simplify this, you get everything 0 except just for the I you get a value, right? So this will be 0. This will be 0 because 0 times any number is 0. If you add them, it becomes 0. And the top, I got again, this will be 0. So I just got overall answer. I got minus 1800 I. And I'm done with this. So, what's up?
K, you put 6 when you cover it, the 6 is going to show you.
No, you see, when I cover K, it just, you get 0 times 300, right? And then minus 0 times 0.
Oh, you put 6.
Oh, no, yeah, no, this is 0 actually. Sorry, yeah, you are right. Yeah, that's a 0. Sorry if I put 6. Because in my brain, it says 0 times any number is 0. So yeah, that's 0 times 0. You are right. So the answer is minus 1800. So let's Again, I talk a little bit about the vector approach. I want to jump into a scalar approach. Then we will do several examples until you get comfortable doing these types of problem. Now, on the scalar approach, which is a different method, again, could be easier, could be more difficult. In this case, I have the force given to me with the plane up there. So the angle with the plane is 3, 4, 5. And then on the plane, I have a 3, 4, 5. Again, it could be, again, this shape here is a little bit small. But what does this mean? This means, if you remember from last session, the one down here, we call that f prime. And this one is fz, because it's parallel to the z-axis. Down here, this one is parallel to y, f of y. And then the last one, this is parallel to x, which is f of x. So in this case, I have to use the ratio method. In the ratio method, if you look into the first one, I have something like this. This side is f prime. That's the shadow. Up here, I have the fz. And then up there, I have the f, which is equal to 500. The angle here is given to me by a ratio, 3, 4, and 5. Again, if you use the ratio, you can say fz is equal to 3 over 5 times 500, which will be 300. F prime is equal to 4 over 5 of 500. This will become 400. So far I have the fz component. I'm going to go to the next triangle down here. In the next triangle, I have a triangle like this. This side is f of y. This side is f of x. And then the hypotenuse is f prime. F prime, we already got it 400. I have the same ratio. I have a 4, 3, and 5. So f of x is equal to 3 over 5 into 400. And then f of y is 4 over 5 of 400. So this will be 320. And this one is 240. The only thing that you need to remember, if you look into this picture, you can see that the force, Fx is actually pointing toward the negative x. So if I retranslate this into, I'm going to say force F is equal to minus 240I. The reason I put minus because this is pointing to the negative. Plus 320Y, which is J, and then plus 300 into the K. So I found the force in I, J, K components. Now what we do in this method, once you found the force, you put them right where they are. So in this case, I have on the Y, I have a force right on the point of action, which is point A. On the Y, f of y is 320. On the x, it's pointing to the negative x. I'm going to put it like this. For this, the amount of force is 240. And on the k, which is up here, I have a force which is 300. So in the scalar approach, once you found the component, you have to put them where they are, right here. Then in the next step, once you put the forces there, you have to create something what I do call it. I do call it, again, it's a little bit look like a table, because for every moment that you do, you have to consider some stuff for it. So let me just to go over a little bit of explanation what's going on. Now we have 3 chairs. In these 3 chairs we have the moment, we have the force, and we have the distance. If I do, again, I want to do moment about point x, I want to do moment about x-axis, y-axis, and z-axis. So when we say doing moment in 3D we do moment about axis. And these are x-axis, y-axis, and z-axis. if I do moment about x-axis, y-axis, z-axis, I need to see what's going on, right? If my force is on, like for instance, I do moment about the x-axis, the force is in the y-axis. The distance will be in the z-axis. So remember, you have three chairs. In these three chairs, in order, again, I have to find the perpendicular distance for each of my forces. Then I need to go through these chairs. I have three seats. In these seats, if, again, there is a seat for x, for y, and the z. Again, I will go over again a little bit more details on this. What do I mean with these seats? But again, we are talking right now about scalar approach. Now you have to look into every forces where they are and then find the perpendicular distance. There are two rules just to keep in your mind. One, if force is parallel to axis, moment is 0. Like for instance, if your force is in the y, you don't need to do any calculation. Moment about y-axis is 0 because there is no way it can produce any moment. And then I gave you the example of the wrench. If you remember, if you apply the force along the wrench, you cannot create any moment. That's number one rule that I would keep in mind. And then if the force intersect axis, moment is 0. So this will help me a lot into my calculation. These two rules, and then some drawing that I have here, that will be helping me too as well. So let's look at here. I need to create a table and I need to consider all those combinations. So what are those combinations? The combination is that how many forces I have? I have three forces, Fx, Fy, and F0. I have the 300, 240, and the 300. So I'm going to put, I have the force 240, which is, this is again on the I. This is just for myself, just remembering that I have a force for 240. I have another force for 320, and that's on the J. And I have the third force 300, and that's on the K. Again, these are just labels for myself, and all the top is labeled. At the bottom, I have moment about the x-axis, moment about y-axis, and moment about z-axis. So for each of these forces, I need to find their perpendicular distance, and I need to find whether they go clockwise or they go counterclockwise. For the force 240, the force 240 is here. You can see it's going back there. I want to do moment about the x-axis. I don't need to think about that. The force is in the x, moment about the x-axis, your moment is 0. Simply, when the force is in x, cannot create any moment about the x-axis. That's it. Now, force 320. The force 320 is on the y. We like to do moment about the x-axis. Where is going to be your distance? So I'm going to go back to here. So I want to do moment about the x-axis. The force that I have is on the y. Where my distance is going to be? Remember, we have only three combinations, x, y, and z. I want to do moment about the x-axis. The force is on the y. Distance will be on? Come on, z. Very good. And then, so now what distance we have on the z? About 0.02 that place. The place of 320, which is here. The distance that we have on the z is the height of 3. So I'm going to say 320 times the height of 3. The question I have from you is that the force up here about x-axis, and then you have to put your eye here on the positive x-axis. Look at it. Does it rotate clockwise or counterclockwise? Like the force is up here, right? I'm looking at force 320, and I do moment about the x-axis, which is here. It is rotating clockwise or counterclockwise?
Clockwise.
It's rotating clockwise. So that's negative, and that negative is coming from clockwise. So remember, if we have 4 forces, you have to do 12 combinations. In this case, I have 3 forces. I do moment about 3 axes. I do a combination of 9. So the force 300, that force is on the z. I do moment about the x-axis. So the force is on the z. We do moment about the x-axis. Where is going to be our distance? So the moment about x, the force is on the z. Where is going to be the distance? Who left? You see x, z, y left, right? Your distance will be on the y. So for 320, what distance I have on the y? Sorry, for 300 here. 300 is on the z, and the distance will be on the y. So this one needs a little bit of like looking at it. So the force is up here, right? And I want to do moment about the x-axis here. Let me just to put my pencil here. This is where the axis is. I'm going to put the pencil so you can see the tip of the pencil. This is actually where the direction of the x-axis is. And then that's where our force is. Right, the force is on the z. I want to do moment about x-axis. Your distance will be on the y. And the y distance is 2. So it will be 300 into 2. The question I have from you, this is clockwise or counterclockwise? Look at the 300 and then you want to rotate about the x-axis. You rotate like this, right? You rotate counterclockwise, exactly. Very good, counterclockwise. So now I can add these two together and I found the moment about x-axis. So if I add those two components together, I'm going to get minus 360. Again, this method is easier, but needs a lot of imagination. The other method is a little bit like more wordy, but is straightforward. This one needs a little bit of imagination and thinking. So I want to do moment about y-axis. So let's go to the y-axis, which is here. That's where the y-axis is. I need to look at every one of them. So the 240. The force 240 here. The force is on the x. We do moment about y. Distance will be on the z. The force 240. Your distance is on the z. So it will be 240 and then distance on the z is 3. The force 240 with the y-axis I have here, this force with that y, rotate clockwise or counterclockwise? Remember, you have to stay in the positive y. Stay here and look at the rotation for the 240. Do you see a clockwise rotation? No, this you see the clockwise. The 240 about y-axis. So this will be clockwise and this will be counterclockwise. Okay, so the next force 320 is on the y. Moment about y is simply 0. I don't need to do any calculation. So the third one I would like to do moment of the force 300, which is on the z. So yeah, the force is on the z. Sorry, the force is on the z. I like to do moment about y-axis. The distance will be on the x. So it will be 300. The x distance we have is 2. Is back there, right? Okay, we need to do a little bit of thinking. So the 300 and the 2. Like the 2 distance is here, 300 is there. This is going to go clockwise or counterclockwise? Counterclockwise, and this will be equal to minus 120. So I go back to the very last one, moment about z, which is this. So on the z, I have two components. I have the force 240, right? The force 240, that's on, the force is on the x, distance will be on the y. So the force which is on the x, I have 240, and then again, the distance is on the y. For the y, I have 2. So it will be 240 times 2. I just need to look at the rotation. The rotation about z is counterclockwise, right? You have to go up there. You have to look at from the top. And that's going to go counterclockwise. The next one is the force of 320, which is this one. I like to do rotation about z. And that one is going to go clockwise. So minus 320, the force is on the y, distance will be on the x. So 320 times 2. And then I can actually summarize my answer. So 240, 300, and then the last one is 0. The answer is minus 1 60. So you can report your final answer that the moment about point O is equal to minus 360I minus 120J minus 160K. I know this will be too much for you to digest, but you will get to know how to do it like in a bit.